Hello and welcome. We are now rolling on with learning R, using R for your day-to-day data analysis. And at this stage, we're going to learn how we can use two variables together. This is very important because this is going to lay the foundations of setting up a strategy of your data analysis. Because most of the times we are faced in a world where we have to deal with more than two variables. However, the principles that we learn in this segment, that of using two variables at a time, will be really useful for you. So we start with two variables, very minimalistic, and then we gradually add more and more variables as we learn, which will be in your multivariate data analysis modules. So what are you going to learn here? You're going to learn how we can take two variables at a time in our software, how we can plot them, and then how we can form a strategy for analysis that will be used in our later modules. So let's get started on this journey. Thanks.
In this particular edition, we are going to learn bivariate data analysis. And this is the first part of the two parts of learning bivariate data analysis in R. By bivariate data analysis, we mean that we take two variables at a time. And what are some of the strategies that we can take? So it's more of a little bit of a theoretical discussion to some extent, but specifically geared towards what can we do when we use R for statistical data analysis. In the first part, we are going to learn a few of the preliminaries that we should be aware of when we are using R. In the second part, we are going to see a little bit more examples and practical implications and implementations of bivariate data analysis. To repeat then, by bivariate, we mean that we are going to take two variables at a time. And depending on a very simplistic classification of those variables, we'll see what are some of the strategies that people have taken, or as an analyst, you can take in order to make sense of the different questions that you may have. So again, this is part of the e-Pathshala concepts that and which we are going to talk about in that context. So basically, we had to do it in four kind of loose conceptualizations. We start with an introduction. We deal with the principles, basic principles. We run, if possible, some demonstrations, and then we summarize things. So basically, the objectives of this particular lesson is to focus on describing the principles of bivariate data analysis. We talk and discuss or describe and almost itemize list, just recapitulate the different types of variables that you will encounter. And some strategies of analysis if you have got a couple of variables, two variables at a time. And particularly how to analyze the two variables at a time in R. Now, the scope of this particular lesson will preclude me from describing these things in much more details or their detailed analytical or theoretical basis. It is more geared towards a convenient kind of conventional notion of what is usually done in terms of analysis of two variables at a time. So before without spending much more words on this, let's start taking a look at the different types of variables that we get to see in our regular routine day-to-day data analytical practices. Now, if we could form sort of a loose classification tree of the different types of variables that we get to see in our data analytical works and processes, you will see that you can largely divide them into two groups. One group of variables are known as, or is known as categorical variables. The other group is known as continuous variables. Oh, and variables, of course, is anything, any entity that can vary in time, over space, anything that shows variation over entities. In the categorical variables, you will see that when we talk in terms of categorical variables, we indicate that a particular entity or a variable will have a number of levels, and each of these levels or each of these of the number of levels will have a distinct entity of their own. For example, let's take the most obvious instantiation of a categorical variable, that of a name. Now, in this world, we have got 7 billion people, and each person has got a name that we can assign to him or her. And that name itself, which will tell you that if name was a variable for everyone in your data set, then that name would have n number of levels. Okay, so but then again, names may have some commonalities. So there are some names that are very common and recur in your data set. So you can say that yes, although in my data set, let's say I have got 1,000 data points or 1,000 rows or 1,000 individuals. These 1,000 individuals by names, maybe they have got like 7 common names that appear. That's almost a far-fetched idea, but let's say that's the case. Then you all say that those 7 names that kind of recur in my data set would be the levels of the variable name. Another, a little bit easier intuitively to understand variable, for example, is gender, male, female. If you consider categorical itself as a variable, then you've got 2 levels, nominal and ordinal. So let's dwell a little bit on the particular concept of nominal variable. A nominal variable basically is a name-like variable. So, each of these levels that we get to see there in the categories, they are kind of self-contained, and each is equivalent of another. There is no implicit rank order imposed in it. But not all categorical variables will follow the same motif. There are other variables, for example, an ordinal variable, in which you have got an implicit rank order imposed in it. So for example, if you were to consider, say, a disease, for example, a disease that has got mild form, intermediate form, advanced form of a disease, or a rank order of say academic performance, poor academic performance, good academic performance, better academic performance than good, and the best academic performance that is expected. Pretty much how we would like to conceptualize and divide our entities, that's how we talk in terms of a categorical variable, and it works for the most part very well. So at one end of the description of our variables, we have categorical variables. On the other end, we have got continuous variables. And continuous variables are the ones in which you cannot have a distinct separation between the levels of those variables. So any variable that has got a measurement that kind of overlaps one with the other will be referred to as a continuous variable. And this has got some practical implications, because for some variable, the intervals alone are enough to define them. For example, if you are looking at temperature being measured in degrees Celsius, then the presence of the figure 0 essentially does not carry any special meaning, because it just means that it is just another temperature point, and you can compare the intervals between. Whereas when you start talking about a variable such as a ratio variable, say an odds ratio, or say for example temperature measured in absolute scale, then that absolute 0 has got a meaning. Basically it signifies there is absence of energy. So the absence of entity that a particular variable that is meant to measure is a very crucial and critical point in terms of doing your data analysis routines. And it is quite important that we should understand that these 4 types of variables, very rough classification, is practically important for our data analysis, and R is sensitive to that. We'll see in a second. Then we move on to the next bit about setting up some sort of a strategies of your data analysis. And when we talk in terms of bivariate data analysis, we need to have some conceptualizations either intuitively or mostly intuitively at this stage, that there are some variables that are treated as an outcome variable. And this is very, very important for you to understand, particularly in the context of different types of regressions that we will see later. The outcome variable, particularly in the context of, say, healthcare or some other fields, is a very important variable whose variability you would like to explain. For example, a very common usage in health services research and delivery, particularly in public health context, is people would like to see what explains length of stay in hospitals or in healthcare facilities. So that variability needs to be explained. So that's an outcome variable. Another very popular or very common outcome variable, rather simplistic to analyze, is death. So a person can die or a person can survive, say, following a surgical operation. So that's an outcome variable. So, outcome variables are the ones in which you learn that certain things has happened and you would like to explain that outcome variable. In order to explain an outcome variable in the context of data analysis, you need to have an explanatory variable. So for example, in case of the length of stay in hospital, you may be interested to find out that maybe age is an explanatory variable. Or you may want to say that a particular type of surgical operation carried out would be better able to explain the outcome, which is length of stay. For example, a surgical procedure done under local anesthesia versus a surgical procedure done under general anesthesia, which is a lot more severe form of, or a much more complicated and much, it's a different form of anesthesia than a local anesthesia. So what happens, of course, is that this is an explanatory variable that you'd like to model, but you're also aware that age may have a bearing on this. So what you would like to do is not only take an explanatory variable, but add a covariate, which means age now becomes a covariate. So you will have one particular variable as an explanatory variable, one or more sets of variables as covariates, and these together will try to explain the outcome variable. This, in general, is a motif of how you would do data analysis. Then there are issues around the role of time. Sometimes time itself is a very important aspect of your data analysis. So some studies or some research are cross-sectional studies. So everything is measured in one point in time. There are other kinds of studies in which variables are measured across time. So time itself becomes a very important variable. And these kinds of studies are known as longitudinal studies. We will take a look at a very, very preliminary look at what you can do in R by way of conducting longitudinal studies. Another way to conceptualize the play of explanatory and outcome variables is to think in terms of the levels of those variables, that is, the types of variables that we are working with. As we had seen, an outcome variable can be a continuous outcome variable, or it can be a categorical outcome variable. Likewise, an explanatory variable can also be a continuously measured outcome variable, continuously measured or categorically measured. So depending on the levels of their measurements, you will have different ways of working with them. This is an important bit where R becomes quite important. One of the first things that we have been repeatedly emphasizing in this series in our studies and data analysis in general is have to have a plan of constructing graphics. So graphically examine your variables. When you start graphically examining your variables, there too, depending on the levels of your outcome and explanatory variables, you will have a number of different things that you can do. For example, if your outcome variable is measured on a continuous scale and your explanatory variable too is measured on a continuous scale, then the plot that you will use for bivariate data analysis to start with will be a scatter plot, which is going to plot the outcome variable and the explanatory variable. We have made scatter plot in one of the earlier modules here. On the other hand, if your outcome variable is a categorical variable and your explanatory variable is a continuous variable, then it is pragmatic that you construct what is known as a box plot. In a box plot, you get to see the median values, you get to see the interquartile range, the extent to which there are outliers, the maximum and the minimum, kind of the range of the values, and you can see them visually side by side as to what happens. And similarly, if your outcome variable is a continuous variable and your explanatory variable is a categorical variable, the same rule applies. That is, you can have a box plot that you can construct. It becomes a little bit more interesting if you have got an outcome variable that is categorically measured and an explanatory variable that is also categorically measured. One of the ways in which you can do that is known as a mosaic plot, in which you can have mosaics in the percentages of the different categorical variables, different categories of the explanatory variable being presented in the various categories of the outcome variable. In this particular set of examples, we are not going to show you a mosaic plot, but I'm going to show you a simpler version of this. That is, after we construct a 2x2 table, or x by x table or n by n table, as the case may be, for categorical outcome variable and categorical continuous variables, we'll start taking a look at a very simple instantiation of a bar plot to see how the different categories stack up one against the others. So this was about what strategies you can take in order to analyze two variables together depending on their nature or their characteristics. So a common way of doing that, of course, would be then we move from a graphical or visual inspection of the data to actual procedures or actual statistics that we can do with them. When you have a continuously distributed variable, which is an outcome variable, and you've got a continuously distributed explanatory variable, your choice of analysis is a very simple correlation plot. So you run correlation analysis of the outcome and explanatory variable. And in running the correlation analysis, you can have something like, depending on, again, the distribution of your variable, whether it's a parametric distribution or Gaussian distribution or not, you can think in terms of constructing what is known as a Pearson product moment correlation, or Spearman's, which is the measurement is using a statistic known as rho. On the other hand, when your outcome is a categorical outcome and your explanatory variable is a continuously distributed variable, then what you need to do is you can, for each of the levels, or let's say if you've only got two levels of your categorical variables, which is the most common scenario, you can have you can construct what is known as a t-test, and depending on how you have conducted your study, your t-test can be a pairwise t-test or an unpaired t-test. If the categorical variable has got more than two categories, you will be conducting what is known as an analysis of variance, or ANOVA, one-way ANOVA. The same rules apply across the spectrum. In other words, if your outcome variable is continuous and your explanatory variable is categorical, you will be conducting either a t-test or an ANOVA, depending on the specific situation. If your categorical variable is if your outcome variable is a categorical variable, and if your explanatory variable is a categorical variable as well, then for just a pair of variables, you can conduct what is known as a simple chi-square test to see whether these variables are somehow related with each other or whether their relationships are kind of independent of each other. You can also conduct some other tests, but for the time being, we're going to focus on chi-square test as one of the tests that you can do. So enough of getting on with some of the preliminaries that we set out to discuss. So it's time that we start talking about putting everything, using a demonstration using R, right? In order to do that, we are going to use a data set which is contained within a package which is known as ECDAT. And within that ECDAT package, there is a data set called Dr. AUS. And basically, this is a study on, doctor visits in Australia in the years 1977 to 1978. They had total number of observations, about 5,000 observations on individuals, and based on Australian studies. So one of the first things that you should do is you should install a package. In this particular case, the package is ECDAT. Then you call the library ECDAT into your R workspace. You load the data Dr. AUS. And then here is an interesting function that you can use in order to examine the number of different things that are present in your the variables that are present in your data set. It's called, the function is names, and then within parentheses you attach the name of the data set. So what it does is that you can see this. Then on the right hand side, you see that you can summarize the data set, and when you summarize the data set, you can see that there are some data that are continuous, there are some that are categorical. For example, the data set called chronic conditions, that is a categorical data set. Or for example, data sets such as the days in which the doctor was seen, that is described as a continuous variable. So to start with, if we take a look at these two variables, hospital days, that is the number of days in which that particular person was hospitalized, and the health score, which was kind of a continuously distributed score that was given to a person based on his or her response to how he or she felt, you can see that you can very easily conduct a correlation. And just one function, it's cord.test, and that one cord.test can give you a fairly good sense of what is the correlation. It gives you the statistic, it gives you the p-value, it gives you a 95% confidence interval, and you can specify what kind of correlation you would like to go with it. So your function is cord.test. You can also use another function called core, and again, very, very similar way in which you can specify the parameters. You can save this function and the functional outputs into an object, and you can manipulate those objects as well. I'll show you another data set, and this data set is on creatine phosphokinase in blood samples of a few people. And the idea was that we wanted to compare whether body weight could explain the creatine phosphokinase excretion. And so the blood creatine phosphokinase versus body weight in athletes. You can see that the body weight is given in kilograms, and blood CPK level is given in the y-axis. And this scattered plot is going to show you that there seems to be a rise in the CPK with body weight. So the heavier the athlete is, the more will be the output of creatine phosphokinase, that is, a muscle metabolite. Reasonable. So outcome is continuous, explanatory variable is continuous. You can use a scatter plot or you could use a correlation analysis. What happens if your outcome is continuous and your explanatory variable is categorical? One way in which you can do this here, in this particular example, we are talking about using the relative lengths of New Zealand South Island rivers. New Zealand has got a North and South Islands. In the South Island, they've got rivers. Depending on where they originate, they can either flow into the Tasman Sea, which lies to the west of the South Island of New Zealand, or Pacific Ocean, which lies to the east. And what we have done is this, that where they're draining into, that's a binary variable, right? So that's a categorical variable. But the length of the rivers, that is, this is kind of a simplistic example where we are going to measure the continuous variable as continuous variable, the length of the rivers and where they're draining. Are they draining into Tasman Sea as opposed to draining into Pacific Ocean? What is the relative lengths of this? So here we've got a continuous variable, length of the rivers. We've got a categorical variable as an explanatory variables or an independent variable or however or indicator variable, which is a binary variable because only two categories here, either draining into the Tasman Sea or draining into Pacific Ocean. So we decided to put together a t-test. And this t-test, as you can see, we first indicate the outcome variable, the length, flows into as the categorical variable, and then we find out the t-test results. You can see that it produces the mean values, it produces a t statistic, and it gives you the p-values. So to sum up, we have just touched the basic surface area of what we would like to do with these sorts of variables, right? So we talked about we introduced the concepts of bivariate analysis. That a bivariate analysis is essentially an analysis of two variables. These two variables can be, both continuous, or one continuous, one categorical, or both categorical. And some simple ways in which we can look at these to continue our exploration. So we stop here and we'll pick up in the second phase of bivariate analysis, where we'll show you a little bit more on how or what kind of R routines we can do to analyze bivariate data in R. Thank you for paying attention to this.
Welcome back. We just learned how you can use two variables, a couple of variables at the most, for learning R and doing data analysis in R. As you learned, one of the two variables is the explanatory variable, which means it is also sometimes referred to as a predictor variable, and this variable is used to predict others. And the other variable is referred to as an outcome variable. In experimental studies, some people refer this particular variable as dependent variable, as if that is dependent on manipulation of an independent variable. So there are certain routines, there are certain things that you can and cannot do with these couple of variables, or how you pair them up for plotting graphs, how you can create different kinds of routines, for example, regression equations, how you can interpret them, etc., etc. In our next module, we will be learning a little bit more advanced stuff as to what we can more do with this. For example, setting up contingency tables, we are setting up some other things. In this module, you learned if both the variables are continuous, what we can do about it. In the next module, we will learn if both variables are of different types of each other, what could be our strategies. So let's get learning. Thank you.